Hi, I'm Saad, presenting my paper Dyna-LfLH, Learning Agile Navigation in Dynamic Environments from Learned Hallucination. In these 3D graphs, we visualize the trajectories of the hallucinated obstacles as well as the robot trajectory over time, with the z-axis representing the time dimension. 3 different hallucination functions that are trained to hallucinate 1, 3, and 5 obstacles are presented. In each graph, the obstacles are hallucinated such that the robot trajectory is made optimal. That is, the obstacles are the reason that the robot needs to execute such an obstacle avoidance maneuver. A 2D visualization of our learned method is also presented. The Jackal robot navigates in an open environment, and our method hallucinates obstacles on this trajectory such that the trajectory is a set of optimal obstacle avoidance maneuvers. The input trajectory to our method is visualized as the green path. It is segmented and passed to our hallucination function. The hallucination function hallucinates 5 obstacles on each input trajectory. Then, the observations of the hallucinated obstacles are rendered as 2D LiDAR scans using ray casting. The motion planner then learns to recreate the original input trajectory using a series of 2D LiDAR scans and a local goal as input. Dyna-LfLH is evaluated on Dynabarn, a simulation testbed for evaluating dynamic obstacle avoidance on 60 different environments with varying levels of difficulty. The easy world environment is shown here, where there are relatively fewer and slower obstacles. However, due to the sudden appearance of an obstacle behind another and the lack of consideration of future dynamics, the 4 other planners collide. In contrast, Dyna-LfLH maneuvered around the obstacle coming from the left side, effectively reaching the end of the map. A hard world environment is also shown. As observed, the number of obstacles, their speed and unpredictability significantly increases. In this case, none of the planners were able to reach the end of the map. Notably, Dynabarn creates extremely dense, unpredictable and challenging environments, with such motion profiles appearing in 50% of the cases. Dyna-LfLH is also evaluated on a physical testbed with 11 iRobot Roombas moving randomly in an enclosed 8.2 by 4.3 meter square arena. Dyna-LfLH outperforms DWA and BC that were best in their category, classical and imitation learning, respectively. Our evaluations on simulated and physical experiments have shown that Dyna-LfLH is capable of generating dynamic obstacle configurations, and a local planner learned from Dyna-LfLH has superior performance than existing classical and supervised learning approaches.